Sorry, do you prefer
Wait.
questions? Okay, sorry.
I'm starting. Okay, so welcome to another live stream for the research. Let's restart. Welcome to live stream for the Assumptions of Physics research program. Today we're trying to do something a little bit different. We're trying to see if by having regularly weekly live stream we can start engaging some people to participate, learn more about the project and so on. The idea is to make this program a little bit more open research, to pull interest and expertise from different places. So the idea is to start having a series of live stream like this. And let's see what happens. So I encourage, if people want to discuss particular topics, to let me know. If I have things that are sort of related to the project, either because they want to learn something or because they are thinking of contributing on something, let me know in the comment, and then we can schedule sort of the next lives to sort of address topic that people are interested in. We also have a Google Calendar that at some point I'll put somewhere with the schedule of what we think we're doing. And so for the first, for today, I thought I would give sort of an introduction to essentially reverse physics and our progress towards the reverse physics of quantum mechanics. So I want to sort of talk a little bit about why this methodology, why we use this methodology, why I think it's important, and then we'll sort of quickly see how it compares to everything that people do in mathematical logic, and then I'll talk about a little bit of what pieces we have in quantum mechanics, what pieces we're missing, and yeah, so if you have questions, put them in the chat. I'll try to follow the chat. Bear in mind that this is, I have a completely new setup to try to use tablets and whiteboard for impromptu discussions. So we'll see how it goes. And if people have suggestion of how to improve, I am grateful, because I kind of don't know what I'm doing. So I'll start just by giving you a sense of what it is that reverse physics is. So one of my problems with sort of approaches to the foundations of physics is that I never got to understand why is it that we had specific mathematical structure and what it is that they represent physically. And the approach of reverse physics sort of came out of that frustration, and I only much later I realized that the type of things that I was looking for are the type of things that people already have been doing for I don't know, 100 years probably, in the foundations of mathematics, which is really zone in on what are the starting points, and in mathematics would be the axiom that you take, and the rules of logic that you assume, and try to really understand what are the relationship, the logical relationship between these axioms that you put in and the theorems that you can prove. So let me share, let's see if this works. Okay, so in principle now I'm sharing part of the screen, and so the type of things that people discuss in the context of set theory mathematical logic is sort of relative strength of axioms and theorems. So for example, this is a picture that I have from this book. I should say what these books are. This is the Handbooks of Analysis and its Foundation from Eric, I don't know, I'm going to butcher the name, Schechter. I have no idea how it's pronounced. It's a very dense book. It's like 900 pages that covers essentially not all of mathematics, but close to it. And one of the things that it discusses is sort of the difference between constructive mathematics and the non-constructive mathematics. And for people that don't know the difference, is that there is this key axiom that people have debated for a long time, the axiom of choice, that basically tells you that if you have a collections of set, you can pick an element from each set. You can make a choice from each of these set. And the interesting part is that that actually has an extra axiom in set theory. It's independent from the standard, from the core of the set theoretical axioms, and it provides some counterintuitive consequences of, so this thing has been studied. And what you see here is the relationship between the axiom of choice, two theorems that are proved to be equivalent to the axiom of choice, meaning that if you take the sort of the base axioms of set theory and you assume the axiom of choice, you can prove one of these theorems, or you can take the base theory of set theory, assume one of these theorems, and then you can prove the axiom. So basically, assuming the axiom of choice is the same thing. And these are sort of all lesser versions of the axiom of choice. So there is the axiom of choice for R, so you can make a choice in subsets of R. I think this is the axiom of countable choice. You have countable in a subset, and you can pick things into there. And so the idea is that by studying the relative strengths of all these possible conditions that you can put, you get some idea of what these theorems are. And this sort of started in the 80s, sort of something like this is also called reverse mathematics, which is a field of study in mathematical logic started by, I'm never going to remember the name, so I shouldn't even said that. Anyway, that basically, again, the idea is you start with this observation that when the theorem is proved from the right axioms, you can prove the axiom by the theorem. And so what people go and look at, for example, this is a book, again, I should probably show what this book is. This is a book called Reverse Mathematics, Problems, Reduction, and Proofs by, again, I'm not going to pronounce the name, Mummert probably, I can pronounce the other one. I really don't know because I just read these things, so I haven't like heard these names. And so anyway, so the point is that even here they have diagrams of that kind. Let's see if I can, there you go. So these are basically different, let's say, subsets, subsystems in mathematics, and again they go by strength of assumptions. So these are more powerful in the sense that if you assume this, then you're assuming all these other conditions, and if you assume this basic set of properties, you're not assuming everything that it's above. And again, you can prove equivalences here. So you can prove that these two together are equal to this, and so on. So of course, I don't know exactly what all these symbols means, but the problem is that there are conditions, and you prove conditions in there. So what is it that we're trying to do? Reverse physics. I basically want to do something like that, right? I want to have a whole diagram with all the possible physical assumptions that we can take and understand how they are mathematically implemented, so that we can say, okay, this piece of mathematics is there to represent determinism and reversibility, and determinism and reversibility is an extra condition that you can put on a law of evolution, because a law of evolution could be deterministic and reversible, or not deterministic and reversible. And so you know exactly then which part of the physics you're describing and which part of the math describe the physics, and you finally get to understand what all these things are about. So, for example, in classical mechanics, we have done some of this work, and we are able to say that you can take, let's see if I can draw, they can take the assumption of infinitesimal reducibility, meaning that you take a system, and the system is made of parts, and the parts are made of parts, and so on, and you can go arbitrarily small, and describing the whole system is equivalent to describing the state of all these infinitesimal parts. And so we call this the infinitesimal reducibility assumption. And then you also have the idea that the system can be decoupled in independent degrees of freedom, so that when you study vertical position and horizontal position, they basically, the states that you can define on one set of variable are independent from the other variables. So you can pick any position and momentum in the vertical direction with any position and momentum in the horizontal direction. That the definition is completely independent. And what we're able to show that these two conditions together, they give you the structure of classical phase space. So classical phase space is actually allowing these two conditions together, and the points of phase space essentially represent the state of these infinitesimal parts that your system is made of. And then you say, okay, I will add, as I was saying before, the assumption of deterministic and reversible evolution, and what we can show is that these two together are essentially assuming Hamiltonian mechanics, so the Hamiltonian law of evolution. And this condition is actually something that we show in multiple different ways. So we have multiple different realization of that condition, either by the equation or by conservation of entropy. There are multiple ways that you can sort of take that condition. And so this condition is really an equivalence class of a bunch of conditions that you can have. And again, by knowing and understanding what are the possible realization, both mathematical and physical, of those conditions, you get more of an idea what's going on. And then you can say, I have another assumption that you're going to call kinematic equivalence, basically the idea that you can go from state to trajectories and from trajectories to states. So if you look at the trajectory, that's enough to know what the state of the system is at all times. And there are two forms of this assumption. One is the weak one, which basically say you can invert from position and velocity and vice versa. And these two together are what essentially give you Newtonian mechanics. There you go. And then if you take dr and wke plus the classical phase space, you put them together, that's what when you get the Lagrangian mechanics. Then you can take the full kinematic equivalence, which is a stronger condition than the weak kinematic equivalence. And all these lines are an implication if you go below. For if you assume Newtonian mechanics, then you're assuming that you have IR and you have RND, so that's basically what we're trying to say. And then if you take the full kinematic equivalence, then on top of all of this, then you're going to get essentially point particles, massive particles under potential forces, both scalar and vector potential. So these are the kind of diagrams that we want to be able to do. Classical mechanics is mapped. It's not mapped in a super formal way because at that point I wasn't trying to do. I just was trying to get something going, and so I'm trying to revisit some of these, let's say, way of methodology of how to do it for quantum mechanics, to make it a little bit more formal and to use some of the language that people use in reverse mathematics to sort of characterize the relationship between these conditions. Because I noticed that doing this kind of work in quantum mechanics is a lot harder, because the relationship between the math of the physics, it's not as nice as it is in classical mechanics. There are basically pieces of math that are there, but they're not really physically represented. So you have to really be careful of what is it that it's physically meaningful and what is not. And so I have been going, you know, a little bit more in detail of how exactly to do this. So that's basically a high-level picture of what we're trying to do, and I thought that next I basically show you what type of conditions I've been coming up with quantum mechanics, some of the relationships, some of the pieces that I have, and some pieces that I don't. But I'll wait 10 seconds or something if people have questions. Yes, Harvey Friedman is the person that, yes, sorry about this. I can never think about the names when I'm put on the spot, and I don't know why I put myself on the spot. Yes, Harvey Friedman is the founder of reverse mathematics, and I actually had a couple of exchanging with him on these ideas. I actually talked also some of the people that do reverse mathematics to get some ideas, and it's funny because the techniques are completely different because they're different, but some of the strategies that you do are still the same. So
I have a
Steve
question.
says that he has some comments about this. Oh, Tobias, you had
Yeah.
something?
So in this diagram, these arrows pointing down are implications.
Yes.
So if you assume Newtonian mechanics, you had to assume classical phase space and weak kinematic equivalence. In that sense, Newtonian mechanics implies these two. But
Correct.
we also have the fact that if you assume both, you have all of Newtonian mechanics. So that's
You're
not
right.
reflected in this diagram, right?
You're absolutely right.
Okay.
Yes.
Okay, just to clarify.
You are absolutely right. Thanks. So these are exactly the type of things that we have to think a bit at higher level, how we can communicate all these things. Yeah.
Well, one other notation that I also saw in the reverse mathematics diagrams was like we would call NM CPS plus WKE, right?
Yes.
Okay, okay.
Yeah. So you can sort of do this, CPS plus WKE.
Yeah.
It's a little bit messy because so in principle. Like if this were like a real Hasse diagram, then like it's a sort of Hasse diagram upside down, because the sort of the zero is on top. Yes, the zero is on top and the top is on the bottom, so it's kind of reversed. So like written as a Hasse diagram, you could argue that an M is the meet, so the end between those two conditions. But technically, you would need to know that the diagram is complete, right? So right now we're not saying that the diagram is complete.
Yeah.
Yeah. So I don't know if Steve, you wanted to elaborate on the comments, or otherwise we can go forward and
Maybe
look at all the other things.
just clarification. So this diagram would equally apply to let's say treatment of systems of particles as well as statistical description. Like statistical
Yes.
mechanics is still included here or not?
Yes.
Okay.
In fact, the infinitesimal reducibility assumption already has a type of statistics, because you are basically like you are assuming that your system is a collection of parts. So in that sense, it's a statistical distribution. It's not a probability distribution, but it's still a statistical distribution.
And then what do we need for probability distributions?
So this is where it's let me think. So there is actually something that I still have to clarify in my head, whether the reducibility is just at the level, can be formulated at just the level of a particular system at a particular time, so that you have a statistical distribution, or it also has to be an assumption of like the ensemble itself can be thought as being made of independent preparation, like that you can actually think of the whole preparation as a probability distribution of other preparations, which is certainly something that you have in classical mechanics and you don't have in quantum mechanics. So there are some key points like that that are not absolutely clear to me. But so yes, that's why it's still something that I think needs to be polished. So.
Yeah. Okay. Thank you. Thank you.
Yeah, I mean, it's still a research program, right? So it's not fully 100% done. But to your point, I think the simplest way would be to have another assumption here, right? So the statistical description could be part of the law of evolution itself, right? So if I don't have deterministic real, but I have something like I don't know what it would be. It wouldn't be non-deterministic evolution, but let's say that you just define an evolution law, right? If you just defining an evolution law, and then of course the determinism and reversibility is just a particular type of an evolution law, but we could have a more general one that includes also statistical descriptions, and so then statistical mechanics would be the structure of classical phase space plus a non-deterministic evolution law, or a general evolution law that would always talk about evolution of probability distribution, and only in the case that where each element of the distribution have a deterministic and reversible motion, that is, you have 100% prediction and retrodiction of each element, then you would have deterministic and reversibility. So in principle, you should be able to see deterministic and reversibility as a special case of statistical mechanics.
Okay, and then another short question. So, since you said that statistical mechanics is included in this picture, so can we say that also some portion of thermodynamics is also already here?
No, thermodynamics should be a separate theory.
A separate.
Yeah, and then you would have some links between. Oh, it's not drawing anymore. Let's go. Okay, now there is. I don't know. There is a delay between when I draw on one side and when it draws on the other side, and then you basically would have a connection between sort of things here and things on the other side. So let me think of a concrete example of where problems are. So when you're doing thermodynamics, right, and you're thinking about macrostate, you talk about all those things without regard to the underlying description. In fact, the people who designed thermodynamics, they did it on purpose to design thermodynamics such that it does not depend on the ultimate description of the constituents, because at the time there were multiple different hypotheses, and they want to say, well, we want to talk about all these things without, independently of the hypothesis, so whatever hypothesis gets confirmed, we don't care. And so it really works like that. So thermodynamics is essentially a theory of equilibria and boundaries, and what happens when you put systems that are equilibrium and you remove some type of boundary, and then you see what happens. And then, of course, there is a connection between statistical mechanics and thermodynamics, in the sense that then you have some rules to say, if I have this macro state variable, they become the statistical average on the microstate description. You have a rule to define your state by entropy maximization, and then you can go in calculation and you can sort of say, okay, the laws for this particular, the equation of state for this particular system, I can derive it from statistical mechanics and so on. And you have this connection both in classical mechanics and in quantum mechanics, because you have both classical statistical mechanics and quantum statistical mechanics, and they both connect to the same thermodynamic infrastructure. And so you want to keep these three theories separate, because you'd like to be able to say, okay, what are the conditions in which I can use both classical statistical mechanics and thermodynamics? What is this concept of equilibrium? And why is it that we define equilibrium in some way in classical statistical mechanics by entropy maximization, for example, and instead we take it axiomatically on the other side by saying that the entropy, there are all these things that needs to be worked out, which of course we haven't worked out. But the idea is that the assumptions of equilibrium and all those things, like, it's unclear to me how they actually play out between the two of them.
Thank you.
Okay, so Steve is asking details on the not-Helmholtz condition in the inverse problem of calculus of variation. I think that would, yeah, that would probably need a more detailed discussion of all these conditions. So we probably wouldn't have time to talk about that. But you know, that could be a topic for another discussion. I'd be happy to go and look at all these details. And I'm, you know, right now, everybody should think that this is, you know, it's research. So it's a set of arguments that we have made. Whether the argument are 100% perfect or not, I don't know, and that's kind of why I want more people to look at these things to make sure that I haven't you know, lost a piece somewhere and so on. So Steve, I think we're gonna go ahead with quantum mechanics, and then we can return to that question in another session maybe. Okay, so. Quantum mechanics. One of the problems that I have in quantum mechanics is really the fact that the mathematical description is further detached from the relationship between the math and the physics is not well articulated. And this is the whole problem that people try to solve with interpretations. And if interpretation were a solution to the problem, probably somebody would have already figured out like 50 years ago. So what we're going to do instead, we want to sort of take these postulates that you have in quantum mechanics to sort of break them down into smaller conditions and try to figure out what is the relationship between these conditions. And one of the ways that I've started to approach this problem, instead of trying to make the whole diagram by, you know, as a whole, I've been trying to break it out into different pieces, and I started this idea of these technical briefs, which are basically very short summaries of the relationship for a single condition. So for example, here we have one of the questions is what is it that the superposition corresponds to in physically, and the issue is that superposition mathematically are just the sum of two vectors. The problem in quantum mechanics is that the vectors themselves do not represent states. It's the rays that represent state. So the question is, what is it that these things are representing, and what is it how we can think it physically? So I have here, these are the type of things that I want to do in quantum mechanics. For example, this is a condition that I call QST that basically tells us what the quantum states are. So the state of a system is represented by a ray of a complex inner product space, and an ensemble is represented by a density operator. And typically the quantum state condition will also include the Born rule, but I didn't need it for this particular instance, so I don't have it here. At some point I will revisit all of this and make sure that all the conditions are the same in every of these technical briefs, and then when they go in the book, there should be sort of a standard formalization of these conditions so that everything agrees. But when you're doing research, you have to play around with things and see where you go. So you have these conditions, then you have a condition that a particular state is a superposition of two other states. And then you have a condition of multiple decomposition of a mixture. So there is a state rho, there is a mixture of psi1 and psi2, and it can also be expressed as a mixture of psi and something else. So rho is the convex combination, a probability distribution over two pure states, psi1 and psi2, and it's also a probability, a mixture between rho, or between phi and phi hat. So the idea is what we want to show is that these two conditions are the same. So this is something that is physically realizable. This we understand what it means physically. We have the same state that it can be produced by creating a statistical mixture between two different pairs of states. And this is not something that you can do in classical mechanics. This is something that you can do in quantum mechanics, but you can't do in classical mechanics. And we want to show that this type of property is exactly maps one-to-one with the ability of creating superposition. And As I said before, superposition are just a mathematical thing. They're mathematical representation. And by creating this bridge, we can have now a physical understanding of what that mathematical description gives you. And this is exactly the type of thing that we want to do in reverse physics. It's when your physical ideas is derived by the correct mathematical conditions, then the mathematical conditions can be derived from the physical ideas, so that you have these equivalencies, and these are the things that we want to do, such that whenever we see this, now we have a physical intuition in the back of our head of what it is, and it also tells us why quantum mechanics is particular with respect to classical mechanics, because in classical mechanics you can't have multiple decompositions in terms of pure states. If you have different pure states and you mix them, you're going to get something different. You can't get the same thing. And then basically we have a theorem, and this is the type of thing that one says in reverse mathematics, and so we are trying to adopt the language in reverse physics so that, again, it feels more and more formal. It feels that, you know, we kind of are knowing what we're talking about. And so you can say that the quantum superposition in terms of pure states and the quantum superposition in terms of mixing are equivalent over a base theory. So once you assume that you have quantum states, picking one or picking the other, they're the same. And the way that the notation we're trying to go for reverse physics is to basically have this equivalence class being the first part of the acronym, and then the particular realization of that in that equivalence class after the dash. So that way that as soon as you see the condition when it's stated, you can understand where we're going, right? These two things are going to be equivalent because you see that they have the same prefix. And this is something that we were already doing in the reverse physics for classical mechanics, but I'm leaning into it a little bit more. And so what you do is just you do a demonstration and you show that if you have one condition, you can find indeed a state that can be decomposed in two ways, and that you can also go back and forth. So this is just a theorem that if you prove, if you assume this, and then from this you can prove this, and this implies this. And so this is essentially what we like to do, and you can see this is just 2 pages. So the idea is that if we break up all of the reverse physics for quantum mechanics into these shorter things, we can work independently on shorter things, then put them all together. And if somebody wants to learn some of these ideas, they don't have to go into a 500 pages book. They can just go to that list of technical briefs and cherry pick the type of things that they're interested in. So just to give you a sense, if I can find, the back button is here. There you go. So other things that we have, for example, that are interesting in the context of reverse physics quantum mechanics, we show that the Born rule is equivalent to the von Neumann entropy. So again, let's go directly to the theorem. If you assume EQST, which basically means you have quantum states and ensemble, so you are not assuming the Born rule, you are assuming that you have quantum states as defined by raising a Hilbert space and ensemble as defined as density matrices. Then you have a condition which is the Born rule, the fact that the conditional probability is given by this formula. The condition that the entropy is given by the von Neumann entropy, and I can see that I'm missing a minus sign here, so let me make a note of that because it's missing a minus sign. So there you go. And then you have a separate condition, which is these are the type of other conditions that we want to find in reverse physics, which are conditions that are sort of more consistency checks and things that every physical theory needs to satisfy. That's something specific to quantum mechanics. So you have 2 conditions here in terms of mutual exclusivity. you can say that two states are mutually exclusive, or a set of states are mutually exclusive if the conditional probability of one given the other is 0. So if I prepare one, I'm never going to measure the other, and vice versa. Then these are mutually exclusive. If I prepare one or I prepare the other, I'm not going to confuse between the two. And then you also have the idea that when you mix a pair, you just sort of mix the entropy, when you make a statistical mixture of those states, you have that the entropy goes up in terms of the Shannon entropy. And that's again a condition that tells you that two things are distinguishable. If you make a 50-50% of two states, a mixture of two states, and the entropy goes up by 1 bit, well, the fact that the entropy goes up by 1 bit is exactly the fact that you can tell one from the other. And so you need this consistency condition that if things are mutually exclusive, then if they must satisfy these two conditions at the same time. The conditional probability has to be 0, and also the entropy of the mixture has to be given by the Shannon entropy. And so what you show then is that if you assume that you have quantum states with, as we said before, the ensembles for the quantum states, then you have these three conditions: the fact that you have the Born rule, the fact that you have the entropy given by the von Neumann entropy, and the fact that you have this sort of consistency conditions. And if you pick two, then you find the other. So typically in quantum mechanics, you assume these two things to be true. Somebody gives you the Born rule, and somebody gives you the von Neumann entropy, and then you can verify that this condition is satisfied. And by the way, that condition is satisfied also in classical mechanics. But you can also say, I have the Born rule, I get the consistency condition, I get the von Neumann entropy. Or I assume the von Neumann entropy, I assume the compatibility condition, I recover the Born rule. So these things are all related to each other, and really what you will want to say is that this is a condition for any physical theory. So if we assume that this is a condition for any physical theory, whenever you take mutex and this, then these two are going to be equivalent of to each other. And so again, these are the type of things that we want to do to be able to have a better understanding of the structure of quantum mechanics. And I'll pause a little bit if you guys want to prepare some questions, but the point is really figuring out what all these pieces are and how they're related to each other. And of course, the more conditions that we can pull together because somebody knows or something else that somebody discovered 30 years ago, then we can put it all together. And I am sure that a lot of these things that I am recovering are things that people already understood, throughout this 100 years of quantum mechanics. But the point is that we never had a sort of a container where to put all these observations and these relationships. And so what happens is that they get forgotten, they get rediscovered, they get forgotten again, and they're never put together. And so if you don't put them together, you don't start having a sense that you're really understanding the theory as a whole in terms of all these pieces. And I think that's why the foundations of quantum mechanics haven't progressed in a way that I think we need, so that you do get this better understanding. Hi, memes. Okay, so any question on this overview?
If I may,
Go
a
ahead.
couple of questions. So one question is, I don't know if you've seen any, let's say, so-called axioms of quantum mechanics. I think there are maybe a couple of sets, maybe written by Feynman or maybe by Hilbert. But what is your how to say, your opinion about them? Like, are they pushing something under the carpet, or like they're based on something not well defined or not physical? Because people, of course, thought about axiomatics of quantum mechanics. So where do you stand on what is usually taken as granted without much thinking?
There you go. So this is going to be, I'm starting to develop also the chapter on the book, and the sketch is going to be, we start by listing these postulates, and then we go and break them down. And one of the issues, so there are a couple of issues that they're never justified. So, the typical postulate, the state of a quantum system is represented by the projective Hilbert space, a state is represented by a ray in the Hilbert space, and an ensemble is represented by a density operator. Like, these are the type of things that people put in the postulate, and there are essentially two ways to characterize this. Some people prefer to define the pure states and then define the density operators on top. Some people instead prefer to define the ensembles first and then find the pure states as the one that cannot be further decomposed. So, but the question is the same. Like, you do not know what you're assuming here, and there are, like, it's too much too quick that you don't know exactly what things are going. So if you say that the state space is represented by the projective space, by the rays, well, here's the thing. To define the rays, I do not need the inner product. If I get a vector space without the inner product, that's enough to define the rays. So what is it that the condition alone tells me? If I just say that the rays, that the states are rays, how much of quantum mechanics do I get? Same thing, if I say that ensemble space is represented by a density operator, now then I will need the inner product because the density operator are a trace one, and the definition of the trace requires the inner product. And so that's an additional mathematical structure. Why is it that you're taking it? What is it that it's doing, and so on? So these are all the pieces that we don't have because you're assuming this whole thing, in the same way, as basically a single unit. There are, different ways. They're called quantum mechanics reconstruction, basically trying to find different starting points. And one of the problems of those different starting points is that there's still a lot of the time mathematical conditions. So there is one like very famous from Lucian Hardy that at some point basically says that sort of the number of the dimensionality of the space is kind of the square, the dimensionality of the observable, it's kind of like the square, I don't know, maybe it's the other side. Yes, the dimensionality of the observable goes like the square of the dimensionality of the space, something like that. And you probably have to go and look at the conditions carefully because I don't remember. But the point is that it's not a physical condition, like why that? What is it doing? And a lot of the time when people do those reconstruction, yes, you have mathematical conditions that are sort of equivalent, but you again don't know exactly where they're coming from anyway. So that doesn't buy you much. And then there is the problem of you're fixing and you're saying that you have a Hilbert space. And the Hilbert space introduces a number of problems. So in finite dimension, all complex inner product spaces are Hilbert anyway, so you don't need it in finite dimension. And in the infinite dimension, where you need it, that's exactly where you get into a lot of trouble by assuming that you have a Hilbert space. And by Hilbert space is you have a completion of the states under Cauchy sequences. And one of the things that I recently done that it's very cute is that if you are in a Hilbert space and you think that that's the right topology and everything, you can create a sequence of states where you have the ground state mixed with a higher energy level. And you can see that we are taking a higher and higher energy level, but with a lower and lower coefficient. So what happens is that when you take the limit for j goes to infinity, the limit of this sequence, this part is going to go to 0, and you just have the ground state. So you would say, as in the Hilbert space, that this sequence would converge and would converge to the ground state. But then if you look at the expectation of the energy level of that sequence and you do the calculation, you see that this is always 1, and the limit of a sequence of a constant is exactly that. So you are in these conditions that if you're using Hilbert space, you're forced to admit that 1, the sequence converges to the ground state, and 2, that its expectation values converges to the first energy level. And that's definitely not what you want in the physical description. And this, again, when you just get the postulate and you get this, right, you don't see the physical consequence, you don't see the physical, the possible physical incongruences there in this definition. And so just by setting mathematical structure at random because one likes them, because Hilbert spaces are nice, because there is the Riesz representation theorem that every dual can be represented. It's self-dual. The Hilbert space is self-dual, so it has nice properties. But yes, okay, it has some mathematical properties, but that might not be the thing that you want. So it's good to have postulate, but we need to go and analyze all these details to see where this postulate come from, and we can only do it if we break these up into the smallest possible condition and understand what that condition gives us, and then do the whole work. Does that answer your question, Julius?
Yes, yes. It was. That's what I'm seeing now. That when I'm comparing the problems you're trying to solve here with the problems in classical mechanics, I see that here there's much more emphasis on these, foundations, of the notions that we should start using, because well, the first thing without thinking is that, let's say if you have this results in classical mechanics, let's say you found this connections between Newton's equation, Hamiltonian's equations, and Lagrangian equations, then why not do the same for Schrödinger equation, Heisenberg equation, and path integrals? Because these are kind of related. But if you say that the problems are already at the foundation of what spaces to use and what states to use, then okay, there's no point in going further with this mathematical machinery.
Exactly. And this is the problem. So I suspect that a lot of the problem that people have with infinities in quantum field theory is because nobody has done the due diligence to look at all these things and dot all the I's and cross all the T's. And so these are not even interpretation problems. It's just the mathematical machinery that we have is not squeaky clean. And there are tons of problems like this. So yeah, it needs to be done.
Thanks.
Okay, let me go through the chat real quick. Steve says that there are a bunch of things that are overlapping between the things that are important to both of us. Good. It's funny because a lot of people that come from the physics have little patience for the mathematical detail, and but as I said, a lot of mathematical detail is either physically relevant or it's actually screwing up the physics. So you have to go and look at this. So let's see. Can valid? Well, you can say A exists. A represents a term. You can say F exists. F you can say F exists. Saturation can represent a different relation. So actually, you can go into the space of reconstruction and count all these the definition of Kazan. There are and you need to ask, are these reconstruction? Yes, so it's yes, like similar things are there in classical mechanics. Like when you write F equals ma, what is it that you're defining? Are you defining the force in terms of mass and acceleration? Are you defining the mass in terms of the force acceleration? And this actually is there for units as well. So you have distance, time, and velocity, right? So it used to be that we had a definition for an experimental definition of units for the meters and the seconds, and we used and the velocity becomes the derived definition. Now what we are actually doing is have a definition for the second, a sort of a definition for velocity in terms of the speed of light. That's what we set. And the meter now is a derived quantity, right? So this is where I had those, in the things that I had before, that I had pick 2 out of 3 type of things. And these are type of relationship that we definitely have in physics whenever we define one things in terms of 2 other things. You always are free to pick which one. In fact, even for the definition of the kilogram has been the same. Like either once you know what the velocity is, you can either define the kilogram and then h bar is a consequence, or define h bar and then the kilogram is a consequence. And now we are actually using h as a definition. That's what it is, and you get the definition of the kilogram as a consequence. So anyway, okay, so I can so all the things that I'm doing right now for quantum mechanics are these briefs and this I'm basically adding a chapter in the last part of the book. So if somebody goes into the draft from the website, they're gonna see all these things that I'm gonna change little by little, because again, I'm crazy, so everything that I do is on GitHub, and every commit exposes all the things that I think at the moment, which might be wrong. But the sort of the idea would be that we start with the postulates, and then we start refining these conditions and figuring out what are the conditions that are actually working. Right now, these are all the conditions that I think I've named. This is the condition for all the quantum states. This is just assuming that the quantum states are raised without knowing that you have that you have an inner product space. So this is just, you just have the complex vector product, the complex vector space. What can you do with this? Then you have the additional of the quantum ensemble density operator, and I think these are all going to be equivalent. So you cannot associate projectors to pure states if you don't have the inner product, because you wouldn't know what projector to associate. You have many projectors and you have to pick the correct one, and so these two things should probably be equivalent. Then the fact that the pure ensembles are the ones that are idempotent, and the ensembles are the extreme points of the ensemble of the convex space of density operator. So I assume that these are going to be equivalent to each other. This is the second iteration. I thought that this was here, and once I finally understood what the problems with. So it's funny because there are a lot of things that I think I know. And then when I force myself to go and look at the details, I actually realize that I don't know. So in quantum mechanics, and in an Hilbert space, you have a canonical way to define projectors, but you could have different projectors. So you could have a something that maps rays to rays that does not conserve the inner product, and so the projectors associated basically change, and they're not the orthogonal projection anymore, and that whole structure sort of destroys itself. But anyway, so these are the things that I think now is my working sort of assumption is that these 4 are equivalent, and then maybe I'll find that they're not, but whatever. Then we found that there was this mutex condition, and I think this is something that it's going to be long-term promoted to something else, so I have a different prefix. And then I have other conditions that I think that are all equivalent to the Born rule. So the fact that the conditional probability is given by the Born rule is 1. The fact that the conditional probability is given by the angle in the projective space, and this is basically how the geometry of the projective space work. This cosine square is really this, so these of course are going to be the same. But again, it gives a more geometric way to understand the Born rule. And I don't know if you've seen in the details of people working on foundational quantum mechanics. Everybody has their own way to derive the Born rule. And this tells you why the Born rule, it's like very obvious and fixed. It's essentially, if you have a sphere, right? and you want to have a distance between 2 points that it's symmetric under rotation, you basically get the angle, and it's basically the only choice that you can have. So if you want to have something that geometrically works as being the conditional probability, you're gonna get that. So it is that. It can't be anything else. Then the other thing that you can say is that the conditional probability is given by the expectation of the corresponding projector. Again, these are just going to be mathematical equivalencies, so they're very easy to show. You can define an inner product between density operators, and at that point that conditional probability is the inner product. So you have this, you have an inner product on the vectors, and that's sort of part of the part that is not really physical, but the inner product with the density matrices is actually physical, and it's the Born rule. So again, it's a different way to look at that. This is the one that I had before, and it needs to be rewritten. Then, as I said before, the von Neumann entropy is the same. And then I have a whole bunch of conditions that they should be equivalent to the Schrödinger equation. So the Schrödinger equation should just be deterministic and reversible conditions. So the same thing that gave us Hamiltonian mechanics in classical mechanics will give us the Schrödinger evolution and unitary evolution in quantum mechanics. And also this gives me a sort of a hope that we could have like a more general theory, that it's a generalization of both classical and quantum mechanics. And then we have a generalization of the Hamiltonian evolution that becomes the generalization of taking the deterministic and reversible motion in this abstract theory. And then if you specialize it in classical mechanics and quantum mechanics, you find the two different laws of evolution. But it allows us to sort of look at a lot of the structure and say, okay, this structure in classical mechanics is exactly the same that you have in quantum mechanics, and it allows you to sort of do the same type of equivalence that we had in classical mechanics. In classical mechanics, we were able to say that Hamiltonian mechanics was essentially conservation of entropy plus independence of the degree of freedom. So we're going to be able to say the same thing, that Schrödinger equation is equivalent to there you go, that the information is preserved, that mutual exclusivity is preserved, that the probability of the probability distributions are preserved. They just move to other observables. This is something that we saw in classical mechanics, and so on. So basically, we have a lot of different conditions, all going to be equivalent, and they're going to give you different ways to understand how to how to look at the Hamiltonian mechanics. And then the projection postulate, I don't have it yet here because there are some things that I still need to figure out, but the idea should just be that you have each of these states should be states of equilibria regarding of some external condition. And so the measurement postulate is basically you're changing abruptly the external condition of the system. And so it's like in thermodynamics, you go from a canonical ensemble to a grand canonical ensemble. You're changing the boundary. And so you're forcing the system to pick one of these different types of equilibria, because if you're in equilibria in a canonical ensemble, you're not in equilibria in a grand canonical ensemble. And these changes, these abrupt changes, are what the measurement postulate is sort of modeling. And of course, if you're changing something outside, you're no longer isolated, you're no longer deterministic and reversible. So there is absolutely no contradiction that you have two laws of evolution. You have one in one case and one on the other case, depending on what's happening on the boundary. And then the connection between the two is that you can see that the time evolution, you can basically recover it as a quasi-static process. So you imagine that you are changing the boundary little by little. Again, like you think about when you do thermodynamics, that you have a quasi-static process, that you're always in equilibrium making small changes, and you can recover, if you assume the projection postulate, the idea should be that you can recover the Schrödinger equation as a quasi-static process. and then you can recover the projection as a unitary evolution of something with an environment that essentially goes. You're basically increasing the entropy of your system by interacting with the environment, and then you recover the projection postulate as a limit, as a the limit of that process becomes the equilibrium of that process, and therefore it becomes the projection because you changed the boundary. So the point should be that you should be able to have these two different conditions of evolution, deterministic and reversibility, and a sort of abrupt, essentially let's call it equilibration processes. So you have deterministic processes and equilibration processes, and then you can see that the deterministic and reversal process is isolated. So it's a series of small equilibration processes, and you can see the equilibration processes as the deterministic revolution of system plus environment that sort of leads to an equilibrium. So that then, if we had that, we would have all the pieces, and then of course we can then play around to find more and more conditions, because when you do this and you understand more the mathematical machinery, you can understand more what other conditions you can use, other conditions you can find, you get ideas and so on. So I think I had talked enough, and we are at the hour, so I'll just opening up for questions and I'll shut up.
Maybe a question from me. So for all these conditions that you seek to show their equivalence, or that one depends on the other, do you think that mathematically, like, the involved notions are the standard ones? Because I remember that I think for generalized ensembles, you were thinking about using these exotic integrals, like Choquet integral, or like fuzzy integral, something like that. So do you think that this also has to be taken into account, or this should be derivable from more like standard
It's
maths?
all gonna be standard textbook stuff. We just need to fix some of the details. So instead of having a Hilbert space, it might be just a complex inner product space. Instead of the observables to be these horrible things that are what are they? They are self-adjoint operator, but they're not defined on the whole domain, and they're not continuous. We need all observable to be self-adjoint and defined on the whole domain and continuous, because otherwise we get nonsensical things like I showed before. The state converges to the ground state, but the observable converges to something different, which is not the expectation of the ground state. That just doesn't make any sense, right? So all these details that need to be fixed, but my goal is to use all the math that people are already familiar with in terms of the vector space representation. And then as a bonus, particularly if I find somebody who can help me that knows more about stuff like the Madelung equation or the quantum mechanics in phase space, because they are different representation of classical mechanics that do not use the vector space, that are also very interesting because they allow you to see the whole theory with a different cut. So if we were able to show equivalence for all these things, then we would get a lot better understanding, because for calculation, maybe some things are easier in the vector space representation, but for other things, for physical intuition, maybe if you look at the Wigner function, it's easier, or stuff like that. But the core is going to be on standard vector spaces with as much as possible the standard notation that people learn when they're doing quantum mechanics. Otherwise, it's completely useless.
Okay, thanks.
And I wondered if some of these equivalent conditions, they are powerful because they connect different perspectives, right? So
yeah.
I wonder if some of them, though, like, are based on different starting points then. So they end up, like, all of these end up with like deterministic and reversible evolution, right? But they would start from different base theories, maybe even, or
So this is where I'm trying to be more precise than what we did in classical mechanics, because in classical mechanics it was kind of the same, and we just added things ad hoc, and it was never clear what each thing implied. But what should happen is that if we're able to show, right, if we're able to say that this mutex condition is something that every physical theory should have, so it's part of the base theory of all physical theories, and then we basically show that if this is assumed and quantum states are assumed, the Born rule is equivalent to the von Neumann entropy, assuming the Born rule is equivalent to assuming the Born entropy. Now we have a single base theory in which we can both prove that the unitary evolution is, let's see, mutual exclusivity preservation, because mutual exclusivity is given by the Born rule, or that it's information preservation because the information is given by the Shannon entropy. So
Okay.
in that case, it would be the same base theory because we proved that within the base theory, those two things are equivalent.
Okay. Okay. Yeah, there was one thing I forgot to say after Julius asked about like if von Neumann tried to justify all these axioms. And I just wanted to say I remembered I started reading von Neumann's book, the original, and yes, he did think, of course, a lot about like how to uh, justify all of this, and he has a section that's literally called like deductive um, uh, this derivation of the theory. I started. The only thing so far that was kind of sketchy was like assuming probability distributions that are not normalizable. So only relative probabilities make sense. And then I know that later, after he wrote the book, he started looking into quantum logic as a different starting point. So he wasn't satisfied with his original approach, I think, and started something new. That's all I know. Just wanted to share that. And the other thing,
Well, let me, since
yeah,
you're changing subject, on that same subject, von Neumann is known that it is known that von Neumann, after a couple of years that he released the book in which the whole Hilbert theory, said that he was dissatisfied, and he started looking at the whole C-star algebras and lots of other structures to basically do
yeah,
things. So he was, like, he's on the record of being dissatisfied with the use of Hilbert spaces, which is kind of ironic. Every time we try to say, look, there are problems here with spaces, there are all these people that says, oh, but von Neumann said this, but von Neumann also said that he didn't like them. So
yeah. Okay, and then what I didn't know, you mentioned something about Hardy and something as a square of the other.
yeah,
I didn't know that reference, but I learned like from this book from these Italian guys that use category theory.
yeah,
Um, this is like the central equation that they derive is also like something is a square of the other. And in that context, the difference is they call one the distinguishability dimension and the other the tomography dimension,
there you go.
which,
Yes,
which
thank you.
is one is telling you how many measurements do I need to make to distinguish two states,
Right.
just to say they are different. That's the smaller one. And the bigger dimension, the square, is the tomography dimension. How many measurements do I need to make to exactly know which state I have? So
Okay.
basically be able to distinguish it from all other states. And in finite dimensions, one is just the square of the other. And this is the central thing they need to derive, and then they find in finite dimension. In GPTs, they find quantum mechanics, basically. But yeah,
Exactly. So that's exactly the thing. I read some of these things like a decade ago, so I completely like it
yeah,
goes. I just remember the one was square of the other, and the other thing that again it can't be a good solution is that, as you said, like it works in infinite dimension, because if I have now a continuum, I have position, momentum, like a continuous quantity like energy and so on. the square of infinity is infinity. It's the same,
Yeah,
so it
sure.
just doesn't work. So, and this is a lot of other problems that people have when they do these constructions. A lot of these things are done in finite dimensions, and they just don't extend to infinite dimension. Or there is the opposite problem that things like the Madelung equation and that is used for many hidden variable interpretations or stochastic mechanics and all this, they work very well in the infinite dimensional case when you have position and momentum, when you have the continuum. But then when you try to use them in finite dimension for spin, they just feel absolutely ad hoc. They just don't work as well. And again, this is whatever we're going to do in reverse physics, we want things that generalize well, that we want structures that you don't even know what you have, if you have discrete finitely many elements or if you are a continuum. And this is where I'll say it for like for as long as I'm here, I'll keep saying that. That's where physics is behind mathematics by 100 years, because mathematics through topology and measure theory has developed ways to deal with integration, derivation, limits, all of those good things in a way that is neutral as to whether you have a discrete space that it's countably many elements, discrete, or you have the continuum, regardless of the notion of limits that you're going to use and so on. That there is these very general ways of doing things that map to experimental distinguishability, as we show in the physical mathematical part of the approach. And so they're not just better mathematically, but they make more sense physically. And so I know that we can have a general theory for all these things that mathematically it's much more nice and precise, but physically make more sense. And it's just not gonna care whether you have discrete quantities, that you have continuous quantities. And my hope is that it's not gonna care whether you have mechanics or field theories, because those are two things that right now there is a big divide. That there is also there in the foundation of quantum mechanics, that not only all these people that work on quantum information theory and so on, the vast majority works on finite dimension, but it's finite dimension quantum mechanics. Then we would have the continuous of quantum mechanics, and then we have field theories. And field theories, bring in a whole other set of issues. So concentrating on finite dimension, it's like such a small piece. So. And Steve says, I tend to think things algebraically. Yeah, I haven't quite understood how to make use of the algebraic intuition, quite frankly. That's something that I still, like the topology, I really am able to use it for limits. I have a lot of intuition from there, but for the algebraic stuff, like the program of doing algebraic quantum field theory, like I spoke to some people and there is a disconnect there that I can't bridge yet. And I don't know if it's because there is a physical reason or because it's just that I haven't created the dictionary yet. I've been slowly creating dictionaries so that I can know how to talk to topologists, to logicians, to people that do quantum information, to people that do quantum field theory. So I'm collecting dictionary. I don't have a dictionary for algebraic stuff yet. So I don't know if there are more questions. Yeah, it is enormous. Like so Steve says, it's understandable that there is, because one of the problem really that has been working against putting all these things together is that the way that I can say um, the incentives work in the academic environment as creating these silos because you want to have the more specialized results and so on. And so it's like I found myself in seeing people that from different fields that were trying to talk to each other and they just couldn't. And oftentimes I would come there and do the translator. And that's kind of the problem because if you don't understand, so all of the foundation of physics is basically the intersection of physical ideas, ideas in foundation of math, in a lot of branches of mathematics. So there is some philosophy and so on. And you need to kind of know what are the important points of each, and you need to know what are the things that are just like details of the other that are not relevant for what you're doing. And even doing that, it's very complicated. So. Anything else on reverse quantum?
I
Bye,
think I said
Steve. Thank
everything there.
you. So I see that Ken Valid is trying to write something. I don't know if it's gonna be something that we can. Let's see. Okay, think about this. Prediction sets. Each set, each here is a set of ideas amongst which one will come through. From you, nobody made a mistake. The particle for the equation, there is not external object turning the thing. There is no uncanny influences. Used to be the actual thing that needs to be correct for you. Oh, okay. So you're talking about realm of applicability. So yeah, so the condition will also work as essentially realm of applicability of the theory. So in classical mechanics, we had this idea of infinitesimal reducibility. That's the sort of the thing that allows us to create a lot of things in classical mechanics. That's exactly the thing that is not going to be valid in quantum mechanics. In quantum mechanics, what we want to have it's the irreducibility, the idea that every state is effectively an ensemble, and all these pure state they are ensembles of things that you can't study further. So you have a statistical description and you can't refine that statistical description anymore. And all pure states are at the same level of statistical description as measured by the entropy. So all the pure states have the same entropy. And the idea should be that by that you should be able to show that there has to be a symmetry between that state space if you want to have essentially evolution over those observables. And once we're able to show that when you have essentially every two-state system has to be a ball, then that's where we can get quantum mechanics. So the trick there, and I haven't started doing that yet, I need to do all the other parts first, is going to be essentially the justification of why do we have the vector space and the space of ensembles as probably as density operators in the Hilbert space. So that's the part that right now I'm kicking the can in the future, but in principle it should be irreducibility that allows us to recover the space of ensembles in quantum mechanics, and then the Hilbert, the complex vector space and all that. Finger crossed, but we're months away for that. Okay, so it's been an hour and 20 minutes. I think it's a good time to stop. Thank you also, Can Valid, for following, and for everybody that has been here, for Tobias and for Julius for participating. And see you next week. So if anybody has specific things that they want to see me discuss, comment, talk about, please put in the description. And I hopefully will figure out by Monday what we're going to do. And bye, everybody.
Bye.